purging. But it probably will be. Okay. Hi, Father Joe. How are you?
Mr. Cooley, could I borrow you for a minute?
Certainly.
All right, new math teacher.
Next man up.
Mr. Sampson Collins.
Yeah.
He walks like something like sexy. He like struts. It's awesome. Ooh. Mr. Cooley, the way he walks, I think he was limping.
Yeah, he was just limping.
He's waddling.
It's because it's so big.
Oh.
Pause.
Man, you telling me I'm wrong? He was. What? Yeah, thank you. Thank you. You got a donut?
I got a
donut. Oh,
No, that's kind of what I thought too, but nope. It was a good, can I see you in the hall?
They're probably not very good. You wouldn't. I have words with the coolest for a minute. I'm like,
I know. Then I saw the goodies out there. I'm like, oh, okay.
I feel like
It's gonna be all right.
warned you. Like, hey, can I see the hallway? It's for a donut, though.
Yeah, when you looked over at him, you looked like, oh boy.
I was just like, that's not common that Father Joe comes and sees you in your room.
This could be it.
Yeah. It's like, oh, we almost got out of math today. Almost. Anyway, so let's start by taking some questions. I wasn't here for our last class, so I imagine you guys probably have some outstanding questions from any place, homework 1, 2, or 3. So I'm happy to take a few minutes here and kind of run through some of this stuff. Jack?
Homework 1.
Yeah.
Any 16 through 20.
Okay.
Probably like 19.
19. Okie doke. By doing some prime factorizations. So negative 24, I can take out the negative 1. And then 24 is 2 to the third times 3. 45 is 3 squared times 5. And 175 is, what does that got to be? Come on, brain. 5 times 35, right? Double check. I don't know. Yeah, okay, good. So that's 5 squared times 7. Oops, I need a negative 1 on there, though. And I'm just going to stick that all under one radical. Okay with that, Jack?
Yeah.
Okay, so my goal, since I have a cube root, is to organize this thing into packets of 3. So I want things to the third power. So right away I see that I have a negative 1 times a negative 1. That'll just give me a 1 and just get it out of here. And then I see that like this 3 to the first and this 3 to the second can make a 3 to the third. And I have that 2 to the third already there. Right? And then if I take this 5 and that 5 squared, that makes a 5 to the third. And then I just have that 7 stuck there at the end. Is that okay?
Yeah.
All right. So these things to the third, because it's a cube root, can all just get pulled out front. And anything left is just left inside the radical. Okay with that? So like these things that are to the third power, because it's a cube root, just get pulled out front.
Why does it go on the 7?
Why doesn't it go to the 7?
Why does like the 7 get cubed?
The 7 doesn't get cubed. That's 7 to the first and then still 7 to the first, because there's not 3 7s, you can't pull it out. has to be to the third power for it to come out because it's a cube root. Okay with that? And then if we just multiply those things together, I have 30 cube root 7. And that's as good as we can do. Yes, but I think Miss Gruden had her hand up.
Oh, yeah. Can you do
Homework 2, number 8. Sure. That's this one, right? Yeah. Okay. By just organizing and taking those 3 coefficients, the 2, 3, and 5, and just sticking those out front. And then 225 is, let's see, 3 times 5 times 7. And I'm going to write all this stuff in blue to remind me that this is the stuff under the radical. 60 is 2 squared times 3 times 5. And 500 is 50 times, or 5 times 100, which is 5 to the third times 2 squared. So again, that's just me doing a prime factorization and sticking it all under one radical. So now I'm going to try to group things together in sets of 3. Oh, my mistake here, guys. 225 divided by 5 is not. Oops-a-daisy. This I did wrong. Let me fix that. Sorry. Yeah. Okay. Sorry about that. So again, I'm going to look for groups of 3. So if I take this 3 to the second and this 3 to the third, I can stick those together as a 3 to the third. If I take this 5 to the second and this 5 to the first, that makes a 5 to the third. I still have this 5 to the third, so I'm going to just copy that one down. And then I have a 2 to the second and another 2 to the second. So I'm going to think about that 2 to the second as 2 to the first times 2 to the first. So if I take those 2 to the second and that 2 to the first, that makes a 2 to the third. And then I just have a regular old 2 left over.
Is that 5 squared?
Which in the red or blue?
Oh, wait. Never mind.
Okay. The red are cubed.
Yeah.
The blue, there's a squared and a cubed. Okay. So now all these things that are cubes, I can take out. So I still have my 2 times 3 times 5 out front. Shoot, let's just call that 30 and just make life a little bit easier. Then I can take a 3 out because of the 3 cubed. Can take a 5 out because of the 5 cubed. Another 5 out because of the other 5 cubed. And a 2 out because of the 2 cubed. Now I'm left with just the 1, 2 left underneath there. So when I multiply 30 times 3 times 5 times 5 times 2, I get 4,500, and then I still got that cube root of 2 stuck there at the end. And that's as good as we can do. You're welcome. Gabby, which one did you want to look at? Number 20 on homework 1. Okay. Okay. So I'm going to start with prime factorizations. So 343 is 7 to the third. Negative 729 is going to give me a negative 1. And then that is 3 to the sixth. And 125 is 5 to the third. Again, I'm doing these prime factorizations in my head. You guys surely probably either need to use your calculator or draw the factor tree or both. Don't feel bad about doing that. Like, it's kind of what I expect. I just, in the interest of time and space, I usually don't draw out the factor trees other than like the first couple of times to show you what I'm doing and then just do in my head from there on out. I don't expect you guys are able to do that also. Okay, just so that's clear. And I just want to point out that 3 to the sixth is really 2 3 to the thirds, right? Okay, so the cube root of a negative 1 is just the negative 1. I have a 7 to the third, so the 7 comes out. I have 2 3 to the third, so 2 3s come out. Then I have a 5 to the third, so a 5 comes out. And there's nothing left underneath my radical. So that is my answer. So 7 times 3 times 3 times 5 is 315, and there's the negative 1 there, so it's negative 315. This was actually kind of nice because everything was a perfect cube, actually. So you could have done this individual, like each of these individually, and still gotten the same answer, which is cool. Who's next? Lily. Homework 2, number 13. Sure. Reese, you are up next. Okay. So, I'm going to start with prime factorizations. Okay with that? 8 is 2 to the third times 11. $208 is 2 to the fourth times 13. 99 is 3 squared times 11. And 63 is 3 squared times 7 times 13. And I see that I'll have some things to reduce, so I'm going to put that all under the same radical. So right away, I see that I can reduce the 11s and the 13s, which is great. Get it out of here! And then I'm going to look to see, I got some stuff to combine. So 2 to the third and 2 to the fourth is 2 to the seventh. And then 3 to the second, 3 to the second is 3 to the fourth, and I still have that 7 down there. Oops. Now I'm going to do some reducing. To do that, I'm going to look for packets of 3. So 3 to the fourth is a 3 to the third and a 1. 2 to the seventh is a 2 to the third, a 2 to the third, and then a 2 to the first. Is that okay, Lily? And you're okay with why I'm breaking them up that way?
Yeah.
Okay. So let's pull some stuff out. So from the numerator, I can take out 2 2s, and I have 1 left under my radical. In the denominator, I can take out 1 3, and then I'm left in my radical a 3 and a 7. Is that cool? Okay, but we're not done yet, because we have agreed that we're not going to leave radicals in the denominators of our answers. So I need to rationalize this denominator. So in my denominator currently, under the radical, I have 1, 3. To get rid of that 3 under the radical, I need to have 3 total 3's under the radical. So I'm going to need 2 more 3's under the radical. So I'm going to multiply the top and bottom by cube root of 3 squared. If I look at the 7 in the denominator, I have 1 7 under the radical. To get rid of that 7 under the radical, I need to have 3 7's under the radical. So I need 2 more 7's. So I'll multiply the top and bottom by the cube root of 7 squared. Lily, are you good with the reasoning there and what I've done?
Yeah.
Okay. If we need to elaborate or whatever, let me know. So 2 times 2 is 4. And then I have the cube root of 2 times 3 squared times 7 squared over 3. And then the cube root of 3 cubed and 7 cubed. So in the denominator, really, I just have 3 times 3 times 7. So when I multiply that stuff out, I get 63. And in the numerator, I have nothing to the third power, right? So nothing can simplify there. So I'm just going to multiply that stuff together. So 2 times 3 squared times 7 squared is 882. And I'll call that my final answer. Is that okay, Lils? Yeah, of course. Reese Peasy. Probably heard that about 1,000 times in your life, haven't you? Are you pro or con? Sure. Number 12 from homework 2 is just the easiest one. Okay, so we'll start with a prime factorization. So that's going to be 2 squared times 3 squared times 5. And 750 is 2 times 3 times 5 to the third. And then 617 is 3 times 7 squared times 11. And I do see some reducing that I can do, so I'm going to stick that under one radical. So those 3's I can cancel. Cool? Okay. Now I'm going to combine stuff together in packets of 2, preferably. So this 5 to the third I'm going to think about as a 5 to the first. So this 2 squared is all fine. This 3 squared is fine. And that 5 squared is fine. All of those can come out. And then I have another 5 squared there, right? So let's take that out. But I have left definitely that 2. And in the denominator, this 7 squared, that can come out. But I'm definitely left with that 11. Reese, are you okay with what I did there? Okay. So the last step then is I just have to rationalize my denominator. So for that square root of 11 to go away, I need 2 11s underneath that radical since it's a square root. So I'm just going to multiply the top and bottom by square root 11. So in the numerator, I have 2 times 3 times 5 times 5, which gives me 150. And then 2 times 11 is 22. And in the denominator, I have 7 times 11, or 77. And that's as good as we can do. So again, I squished some steps together there. Were you okay and able to follow what I was doing? If you weren't, you can feel free to ask and I can elaborate more. But as we get going, I kind of start condensing things because that's kind of what we'd like to do, right? We're going to start off being super specific and showing a ton of work. And as we get going and more comfortable with kind of what's going on, we're going to start combining steps and doing a little less writing and a little less writing until we're at like, you know, a place where I'm able to communicate with you guys what's going on and maybe showing less work than I'd expect you guys to show, but still enough work to where you look back and you're like, okay, like I get what he did here. You know what I mean? Yeah. Yeah. That's what my daughter says. Yeah. It's her favorite word. Anyways, who's next? Grudes. On which homework?
Oh, sorry.
Homework 2. Okay. All right. So I'm going to start with prime factors. And 98 is 2 times 7 squared. Cool with that? I'm now going to reduce each of these radicals individually. So I see in each one of them I have something squared. So each one of those can reduce. So that's going to be 2 root 3. And then I'm going to have 5 times another 5 root 2 minus 10 times 7 root 2. Cool with that? 5 times 5 is 25. 10 times 7 is 70. And these guys, because they're both square roots of 2, are like terms, so we can subtract them. 20 minus 70 is negative 45. Square roots of 2. But here, the square root of 3 and the square root of 2 are not like terms, so there's nothing I can do with those. So that's just going to be my final answer. Is that okay, Elizabeth? Yeah, no problem, dude. So again, you can't add or subtract any radicals. They have to be exactly alike. So just because you have 2 square roots doesn't mean you can add or subtract them. They have to be the square roots of the same number in order for us to add and subtract things. Anybody else before we take our next step forward? Okay, these were good questions. Again, don't feel like you can't ever return back to this material, or we can't return back to this material next time. It's still going to be okay if you want to go back and talk about some of these next time we meet, if you get a little bit further through the homework or whatever, and that's all fine. Whoa. Okay. So today, what we're going to be talking about is multiplying and dividing unlike radicals. So our goal for today is to figure out how to do something square root of 2 times the cube root of 2. Okay, so when I say unlike radicals, I mean radicals with a different index, but possibly the same part underneath the radical. That number underneath the radical is called the radicand. Not really important, but I'm going to probably end up saying that word at some point during the lecture. I don't want anybody to be confused. When I say radicand, I'm just talking about the number underneath the radical. So that's our goal, is to figure out how to do a problem like that. To this point, we've only multiplied or divided things that had this same kind of radical, right? That they were both square roots or both cube roots, but we haven't done one of each. So to do that, we're going to have to introduce a new definition for a radical. So this says the nth root of a to the m is equal to the exponential a to the power m over n. So this is like our radical form. And this one would be our exponential form. And this is going to be quite helpful for us because there's a lot more properties that we have to work with when dealing with exponentials than we have with radicals. So common to the kind of problem we'll start doing is we'll start in something in radical form, convert it to exponential form, use some properties of exponents to combine things together, put it back into radical form, maybe have to do a little bit more simplifying there, and then we'll be at our answer. So before we review those properties of exponents that we'll be using, let's just look at a couple and just translating back and forth between exponential form and radical form. Oh, let's do this. So let's say we just want to rewrite these radicals into exponential form. The first one we'll look at is the square root of 2. So if I look at my definition above, I need the value for n. What number is the index of a square root that we never write? What number is there? Not 1, 2. It's a square root, right? So that number is always a 2. And then we need our exponent. What number is attached to the exponent of that 2 that's always there but we never write? That is a 1. Oops, that looked wrong. So this just becomes then 2 to the 1/2. We okay there? All right. Actually, let's reverse that. Let's make this so let's say we have the 9th root of 3 to the 3rd. So this would be 3 to the 3/9. And notice that 3/9 reduces to 1/3. which just as an aside is the same thing as the cube root of 3. Let's do one more. Let's do the 8th root of 16. What do you notice about this one that's different than the previous? The 16 is not prime, right? So before I get going here, I'd want to do a prime factorization for 16. That's 2 to the 4th. And now I'd be wanting to apply my property. So that's going to be 2 to the 4/8, which reduces down to 1/2. And just as an aside, that is the same thing as the square root of 2. Do we feel okay converting from radical to exponential? Basically, we're just kind of using that property, right? Let's go the other direction and do a couple of examples. So here I'm going to give you something in exponential form and ask you to write in radical form. So let's say we have 2 to the 5/7. Well, the denominator in our exponent tells us the index for our radical. So this is a 7th root. And then the exponent on our 2 is going to be the numerator for our radical, which is 5. And then if I type 2 to the 5th into my calculator, that's just 32. Feel okay on that one, my peeps? Let's do one more just to make sure, and then we'll review some of our properties for exponents and get rocking and rolling here. So 3 to the 7/4. So again, the denominator in our exponent tells us the index for our radical. So this is a 4th root. The numerator of our fraction tells us the exponent. But hold on. What do you notice about this? Notice that the exponent is bigger than the index. So there is some simplifying we can do. Right? I can think about 3 to the 7th as a 3 to the 4th and a 3 to the 3rd. Since our index is index is 4, this 3 to the 4th can come out. And I'm left with 3 times the 4th root of 3 to the 3rd. And 3 to the 3rd is just 27. Is everybody okay with what we did there? Okay. Let's take a few minutes and we'll review some of our properties of exponents that we've kind of developed over the course of your mathematics education. We'll consolidate these into one place. I'll do some little trivial examples to show you why these properties are true. I think that's important to always kind of make sure that we're justifying and understanding like why this property works or that property works. But I'll just do some little trivial examples. We won't prove anything. So this first property says if I have a to the n times a to the m, that's going to be a to the m plus n. So if I have 2 squared times 2 to the third, 2 squared is 2 times 2. 2 to the third is 2 times 2 times 2. And that's just going to be 5 2's, so it's 2 to the fifth, which is the same thing as 2 plus 3, right? Everybody's okay with that? That's a common one that students are always like, oh, do I multiply the exponents or add the exponents? If you just think back to your definition of exponents, it's pretty clear that it's an adding situation. The next thing is the exponent of a product. So if I have two numbers multiplied together to the nth power, that's going to be each one of them to the nth power multiplied together. So if I think about 2 times 3 squared, that's 2 times 2 times 3, which is 2 times 2 and then 3 times 3, or 2 squared times 3 squared, which is exactly what we're seeing in the property. Everybody's okay with that idea? The next one is an exponent of an exponent. So a to the n to the m is equal to a to the n times m. So think about 2 squared cubed. So 2 squared cubed is 2 squared times 2 squared times 2 squared. And each of those 2 squareds is 2 times 2 times 2. That's 6 total 2's, which is 2 times 3. Everybody okay there? All right. The next one is the quotient of two exponentials. So if I think about this as like 2 to the fourth over 2 to the second, well, 2 to the fourth is 2 times 2 times 2 times 2, and 2 to the second is just 2 times 2. So I can reduce those, and I'm left with 2 squared, which is 4 minus 2, right? Is it helpful when I'm doing these little trivial examples to kind of show you why the property is working? I think that's really important that you're seeing that, like, okay, we're not doing anything fancy here. It's just like streamlining things that we've already done to make our lives a little bit more convenient. What else do we have? So a over b to the n is just a to the n over b to the n. And again, this shouldn't be much of a surprise. Like 3 over 2 squared, just 3 over 2 times 3 over 2. So when we just multiply across, we have 3 squared over 2 squared, right? So these little things that I'm doing on the side here are not like how I would use the property. It's just literally showing us why this property works, right? We're just kind of using our basic definition of what an exponent means to show you why these shortcuts are working. We'll do some actual examples with this stuff in a moment. Oops. So the next one is a to the 0 is equal to 1. This one's a little bit trickier to see. So I know 1 is the same thing as like a to the first over a to the first, right? No arguments there. If I use property 4, that would be a to the 1 minus 1, which is a to the 0. So there we can trivially see that, okay, sure, the 0 power just means it's going to be 1 for everything except for 0. 0 to the 0 is undefined. But any other number to the 0 power is 1. And then our last property is the negative exponent property. Okay, so say like we have 2 to the negative 2. Negative 2 is the same thing as 0 minus 2, right? Then if I use property 4, that's like 2 to the 0 over 2 to the second. And using property 6, 2 to the 0 is just 1. So there's my 1 over 2 to the second. Again, just showing you kind of why this property is true. Those last two are a little bit trickier because we have to really had to use other properties to justify that. We couldn't just use like our definition of an exponent. But like, it's not that big of a deal. Okay. So these are going to be super important for us. So I'm going to make sure I, like box these up and put like a, bold face or whatever in my notes, because I'm going to go back and use these a ton in the upcoming homeworks, along with this definition are going to be my main tools to be doing these problems coming up. So you definitely want to kind of highlight those and keep them in your mind, or if you want them open so you can see them on the same sheet of paper you're doing your homework on, or right next to it or whatever, that's probably a good idea. So let's revisit this problem that we started with at the beginning. So we have the cube root of 2 times the square root of 2. And I'm going to walk through this super slow and super deliberate and write down a lot of work. Okay. Eventually we'll start condensing some steps, but we're not going to do that until the second time talking about this subject. I'm going to be really deliberate and like write a lot of stuff down, so don't be freaked out. We'll shorten it up eventually, but for right now I think it's extremely helpful that we're kind of showing all of the work, and you guys get to, until you get a good feel for what's going on, that we're not being sloppy with what we're doing. You know what I mean? Joey? Of course. So I'm going to start by converting each of these into exponential form. So remember, the exponent here is 1, even though it's not written. The index here is 2, even though it's not written. And the exponent there is 1, even though it's not written. So that's 2 to the 1/3 times 2 to the 1/2. Notice when I'm writing these, I'm really trying to go out of my way to make sure that those fractions look like exponents. One thing I see students often get confused at is that halfway through the problem, those exponents turn into mixed numbers. So 2 to the 1/2 turns into 2 and 1/2, and then things really start going off the rails. So try to be careful with that. So this looks like property 1 to me, right, where I have a to the n times a to the m. So this is going to be 2 to the 1/3 plus 1/2. We okay there? So to add the fractions 1/3 and 1/2, we need a common denominator. What's the least common denominator between 1/3 and 1/2? 6, right? So I need to multiply 1/3 by 2 over 2. And I need to multiply 1/2 by 3 over 3. That's going to give me 2 to the 2/6 plus 3/6. And when I add those fractions, I add the numerators, but the denominator stays the same. That gives me 2 to the 5/6, which I then can convert back to a radical. So the denominator of the fraction is the index for my radical. The numerator is my exponent. And then if I go to my calculator, 2 to the 5th is 32. And I'm done. So kind of surprising, the cube root of 2 times the square root of 2 is the 6th root of 32. Probably not what we would have guessed, right? But using the exponential form, this really kind of goes pretty smoothly. Maybe there's a lot of steps here, or a lot to write the first time through, but all we're doing is kind of using our properties of exponents to kind of clean this up till we can get it back into just a single exponent and then rewrite it as a radical, which is not so bad. Let's do divided by cube root of 2. So we'll start the same way. I'm going to convert these into exponentials. So square root of 2 is 2 to the 1/2. And cube root of 2 is 2 to the 1/3. Just using our definition. Cool there. This looks now like property 4 to me, where I have a to the n over a to the m. Property 4 says that we subtract the exponent. So to do 1/2 minus 1/3, again, I need a common denominator. The least common denominator is 6, so I'll multiply the 1/2 by 3 over 3, and the 1/3 over 2. That's going to give me 2 to the 3/6 minus 2/6. 3/6 minus 2/6 is 1/6. Again, you subtract the numerators, but the denominator stays the same, which I can then convert into a radical. The denominator of my fraction is the index for my radical, and the numerator is the exponent. So this just becomes the 6th root of 2 to the 1st. Or if you wanted, you could just write it as the 6th root of 2. Pedro. Yes, sir? Is everybody okay there? What's a little bit more complicated is if we did instead the cube root of 2 over the square root of 2. And you might think to yourself, why would that be any more complicated? Let's just kind of check it out and see why. So again, I'll start the exact same way. Convert these into exponential form. I'll use property 4 to subtract the exponents. I'll make the same common. So 2/6 minus 3/6 is negative 1/6. And I'll pause here and let everybody writing down catch up a little bit. But this is different than the previous one, right? So I have a negative exponent. I have a property that deals with negative exponents. That was property 7, the last one that we wrote down. It says that I get the reciprocal, so I get 1 over 2 to the 1/6. Okay. And then, okay, well, I'll just convert that into radical form over the 6th root of 2 to the 1st. Oh, I have a radical in my denominator. So what do I have to do here? Yeah, I need to rationalize the denominator. How many 2's do I need for a 6th root of 2 to cancel out? I need 6 total. I have 1, so I need 5 more. So I'm going to the top and bottom with. Oh, that went too far. So the 6th root of 2 to the 5th over, so that's the 6th root of 32 over 2. Yuckaroonies, that took a while, huh? Let me present an alternate track that we could have done for this problem that's a little bit more efficient. Now, there's no way you would think of to do this on your own until you've done a bunch of these and realized, like, fiddlesticks, like, this is just going to take forever. But if I look at this step and notice that the exponent in the numerator is less than the exponent in the denominator, 1/3 is less than 1/2, right? If you're not sure, convert them into decimals and then compare them. It's really easy there. Sometimes you could end up with something like 5/12 and 3/7, and heck, I don't know which one is bigger than which there without actually, doing some arithmetic. I'm not, like, that's not super duper clear. Those are pretty close. But here it should be pretty easy. So instead of even doing anything in the rad form, I'm just going to rationalize my denominator right now. I'm just going to start with that step. And then we'll convert things into exponential form and go from there. 2, I just need to multiply the top and bottom by square root of 2, right? Let me do a different color to show that that's not part of the actual problem. Everybody's okay with that? So the denominator is just 2 now. And the numerator, I can approach just like I did the work in part A, right? And so I'm just going to do that. Since we already have the work for part A written down like 2 lines above, I'm not going to write it all out again. But that, to me, seems a little bit easier than going through all that other rigmarole. Is if I just rationalize the denominator first, it just becomes a multiplication problem. That's usually a little easier to deal with than doing the division and then the reciprocal thing and rationalizing to end up at the same place. I think that way to rationalize first is sometimes going to be better choice. And what I noticed to indicate to do that was that the exponent in the numerator was less than the exponent in the denominator. That's kind of what I was looking for. The good news is, even if you miss that and you do it the way we did in the beginning, you'll still end up with the same answer. You've just taken the scenic route. And that's not bad. The scenic route usually takes a little longer, but you have some nice scenery along the way to look at. You got to do a lot of mathematics there, which is nice, right? So no big deal. Let's do another here. Let's do cube root of 18 times of 54. Actually, let's make that 12 instead of 54, or instead of 18. Okay. So what's decidedly different about this problem than the previous ones? The parts under my radical are not primes, right? What do I need to do to start? Prime factorization. So 12 is 2 squared times 3. And 54 is 2 times 3 to the 3rd. Everybody's okay there? I'm now going to use my definition to convert these into exponential form. since the radical applied to the whole thing, I basically have like a 1. And I basically have that sort of situation. So that's where the 1 is coming from. Right? Everybody can see that? Okay. So then I'm going to use my property 2, where I have the exponent of a product. Everybody okay there? So that's just using property 2. Twice, really, right? Because I had 2 sets of parentheses there. I applied property 2 once with the 1/3 and again a second time with the 1/4. Now I see I have 4 property 3s where I have the exponent of an exponent. So when I have the exponent of an exponent, I multiply. So to multiply 2 fractions, we just multiply straight across. So I'm going to fractions over 1. I have 2 to the 2/3, 3 to the 1/3, 2 to the 1/4, and 3 to the 3/4. Everybody okay there? So these 2 we can multiply together using property 1. And these 2 we can multiply together using property 1. We okay there? To add those fractions, 2/3 plus 1/4, we need a common denominator. The least common denominator would be 12. So the first fraction I'm going to multiply by 4/4, and the second one by 3/3. Same situation over here. My LCD is is 12, so I multiply by 4/4 and then 3/3. So I have 2 to the 11/12 times 3 to the 13/12. So far, so good. Let's convert these back into radicals now. So I have the 12th root of 2 to the 11th times the 12th root of 3 to the 13th. Notice, though, on the second radical that the exponent is bigger than the index. So that tells me that I can reduce that radical. So I'll think about that as 3 to the 12th times 3 to the 1st. So I can take out a 3. Still have the 12th root of 2 to the 11th. And I have the 12th root of now 3 to the 1st. Everybody's okay with that? And since these are the same radical, they're both 12th roots, we can put that stuff all together. And if we multiply 2 to the 11th times 3, we get some big honking number. 6,144. Yeep. Again, I promise these problems will get shorter once we get some more experience on this and we start condensing some steps. They're not always going to take this much time, but I want to be really deliberate and really clear about what I'm doing on each step. So I'm doing like the minimum amount of stuff I can do on each step and showing exactly what it is I'm doing so that it's super clear what I'm doing and why I'm doing it and how I got to the next place, because we haven't done this before and I want to make sure that we're being, you know, trying to be as clear as I possibly can about how I'm doing or what I'm doing. You know what I mean? So don't get freaked out. We'll condense the work down eventually, but I think it's super important that you can see like all the little gears turning and stuff before we start like making a machine, right? The machine seems really complicated if you just look at the machine, but if you know how everything is working, it's like, oh, okay, of course it's gonna, you know, I don't need every little gear. I can just see what's gonna happen. So again, we did a lot to do that for what it seemed like a fairly simple problem. Let's see. Let's just stop here. You know what? This has probably been, that's probably far enough.